Assalamu alaikum. Today we will discuss polynomial rings. Before coming to the concept of polynomial rings, let's recall few definitions. So the first definition I'm going to recall is that of an entire ring. So entire ring. So a ring R with identity is called entire ring if R does not contain zero divisors. So a ring R with identity is called entire ring if R does not contain zero divisors. And examples are, we know that the ring of integers does not contain zero divisors. Ring of real numbers does not contain zero divisors. So examples are Z, the ring of integers, R, the ring of real numbers, Q, the ring of rational numbers, and C, the ring of complex numbers. These are entire rings. Second definition I am going to recall is that of a Devian ring. Devian ring is also called skew field. So a ring R with identity is said to be a Devian ring. A ring R with identity is said to be a Devian ring. R skew field. If every non-zero element of R is a unit, if every non-zero element of is a unit. Unit means it is invertible or it has multiplicative inverse. That is, for any A belonging to R, A is not equal to 0, it has to be non-zero element. There exists an element, we write it mostly as A minus 1 in the ring R such that A multiplied with A inverse is equal to A inverse multiplied with A, and this is equal to multiplicative identity, which we denote by 1. And examples of division ring are the ring of real numbers, Q the ring of rational numbers, C the ring of complex numbers, and H the ring of Hamilton quaternions. The ring of Hamilton quaternions. So these are division rings. From these division rings, or the ring of real numbers, this is commutative. Q the ring of rational numbers is commutative. C the ring of complex numbers is commutative. But H the ring of Hamilton quaternions, this is not commutative. However, this is division ring. So the division rings which are commutative are called fields. So in fact, ring of real numbers, or this is a field, Q is a field, C is a field, H is not field. So we come to next definition, and that is definition of field. So field. So definition is just simple as I have just described. A commutative division ring is called field. A commutative division ring is called field. Please note that field is a very important concept in algebra. So it is better to understand it in detail. So let me note it that it is desirable to write the definition of field in detail. It is desirable to write, because this is very important concept. You will come across this concept again and again while studying algebra. So it is advisable to write the definition of field in detail. So we do that. Let's define it again. Definition. So a set F with two binary operations. Since we are going to define field, and the word field starts with letter F, so we denote field mostly by letter F. So a set F with two binary operations we denote one binary operation by the symbol addition, and second binary operation we denote it by dot. We call it multiplication. So is called field if It is tradition that when we write binary operation with this particular symbol, its identity is denoted by the symbol 0. And when we write a binary operation with this particular symbol, mostly we do not mention this symbol and use the addition of juxtaposition anyway. So for this particular binary operation, the multiplicative identity, in fact the identity with respect to this binary operation, is denoted by symbol 1 anyway. So a set F with binary operation, this plus and multiplication, is called field if, let me write the conditions. So conditions are, so first of all, F is abelian group under addition. F is abelian group under addition, and you know what does abelian group means. And secondly, F has to be closed under multiplication. So this is the way we will say it. AB belongs to F for all AB belonging to F. So this is the first condition for multiplication. Secondly, multiplication has to be associative, and that is A multiplied with product of B and C is equal to product of A and B multiplied with C, and this is again for all A, B, C belonging to F. So for multiplication, these are the two conditions. And thirdly, multiplication has to be distributive over addition. So this is what we mean. A multiplied with B plus C is equal to AB plus AC, and B plus C multiplied with A is equal to BA plus CA, and this has to happen for all A, B, C belonging to F. So these are in fact distributive laws. So the conditions I have written so far, these conditions make F into a ring. And now we come to other conditions in order to make F a field. First condition, F must contain multiplicative identity. So there must exist one belonging to F such that one multiplied with A is equal to A multiplied with 1 is equal to A for all A belonging to F. So this is existence of multiplicative identity. Then we must have inverses of non-zero elements. So for any A belonging to F, for any A belonging to F, A not equal to 0, there must exist an element, we denote it by A inverse belonging to F, such that A multiplied with A inverse is equal to A inverse multiplied with A is equal to multiplicative identity, which is 1. And thirdly, AB is equal to BA for all AB belonging to F. This is commutative law for multiplication. So all these conditions make F into a field. So all these conditions together make F a field. So having said that, another way of defining a field, let me write it as well. So another way of defining a field, let me put it number 4. So another way of defining a field. So we may define field in this way that first of all, a set F with two binary operations, addition and multiplication, is called a field. A set F together with binary operations addition and multiplication is called a field. If so, we can say that F is a field if first condition we are going to impose is that F is a abelian group under addition, the same condition. So F is a abelian group under addition. Secondly, if we remove identity with respect to addition from the set F, that is F minus 0, non-zero elements of F. So F minus 0 is a abelian group under multiplication. So please note it very carefully. Before saying that it is a abelian group under multiplication, we have removed additive identity from F. So second condition is F minus 0 is a abelian group under multiplication, and the third condition is the distributive law, and that is A multiplied with B plus C is equal to AB plus AC, and this has to happen for all ABC belonging to F. So please note that in this case, when we have said that F minus 0 is a abelian group under multiplication, it is sufficient to write only one distributive law, because other distributive law will automatically hold because of commutativity of multiplication, which we have required in second condition. So let me put a note to this effect. So in above definition, it is sufficient to mention in above definition, this definition, in above definition, it is sufficient to mention only one, say, left distributive law. So it is sufficient to mention this distributive law: A multiplied with B plus C is equal to A multiplied with B plus A multiplied with C for all A, B, C belonging to F, because the right distributive law would also hold because of commutativity of multiplication. Because of commutativity of multiplication, So when we write definition of field, we mention only one distributive law because other distributive law automatically holds because of commutativity of multiplication. So having said that, let's come to some examples of field. So examples. So first example are the ring of real numbers, Q the ring of rational numbers, C the ring of complex numbers. These are fields. Secondly, ZP, let me explain it. ZP is equal to 0, 1, 2, so on up to P minus 1, where P is prime. Where P is prime. This is always field under binary operations. Addition modulo P and multiplication modulo P. To see it easily, let me give you an example to understand this. Consider Z7. 7 is a prime and Z7 is equal to 0, 1, 2, 3, 4, 5 and 6. These are in fact equivalence classes, but however, with binary operations, addition modulo 7 and multiplication modulo 7. So consider Z7 with these two binary operations. Then first of all, we consider Cayley's table for addition modulo 7. Then Cayley's table for addition modulo 7, and you know this table very well from our previous work. So this 0, 1, 2, 3, 4, 5 and 6. This is addition modulo 7. And then 0, 1, 2, 3, 4, 5 and 6. And you know the table. This is 0, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5. And then 6, 0. And then 2, 3, 4, 5, 6, 0 and 1. Then 3, 4, 5, 6, 0, 1 and 2. Then 4, 5, 6, 0, 1, 2 and 3. Then 5, 6, 0, 1, 2, 3 and 4. And then 6, 0, 1, 2, 3, 4 and 5. And you can see from this table that Z7 is abelian group under addition modulo 7. You can see everything. It is closed under this particular binary operation. 0 is the additive identity, inverse of every element you will find in it. And you can check the associativity by inspection. So from this table it is clear that from this table it is clear that Z7 is abelian group under addition. In fact, what I must say is that under addition modulo 7. So this is abelian group under addition modulo 7. Now we draw Calais table for Z7 minus 0. So now we consider Calais table for this particular set Z7 by removing 0 from it. And we are going to do it under binary operation multiplication modulo 7. So let me construct the table. So operation is multiplication modulo 7 and elements are 1, 2, 3, 4, 5 and 6, and the same goes along the column 1, 2, 3, 4, 5 and 6, and you can check it. It will be 1, 2, 3, 4, 5, 6, and then 2 multiplied by 1 is 2, 2 multiplied by 2 is equal to 4, 2 multiplied by 3 is equal to 6, 2 multiplied by 4 is equal to 8, and 8 will be 1 under a multiplication modulo 7, because when you divide 8 with 7, remainder is 1, and other elements I just write, you can check on your own. So 3, 5, and then again 3 into 3 is equal to 3, then we have 6, 2, 5, 1 and 4, and then for 4 we have 4 to the 8, we will get 1, 5, 2, 6 and 3, and then 5 ones are 5, 5 twos are 10, 10 modulo 7 will be equal to 3. So 3, then 1, 6, 4, and 2, and then 6 into 1 is equal to 6. 6 into 2 is equal to 12. 12 modulo 7 is equal to 5. And then 4, 3, 2, and 1. And you can check that. This table shows that Z7 minus 0 is closed under binary operation multiplication modulo 7. 1 is the multiplicative identity, and you can see that inverse of each element exists. Associative law can be checked by inspection. So the table shows that Z7 minus 0, Z7 minus 0 is closed under multiplication modulo 7. So this is our first observation. And secondly, we observe that 1 is identity with respect to 1 is identity with respect to this particular binary operation, which we have denoted by this symbol, multiplication modulo 7. And thirdly, about inverses, we know that 2 and 4 are inverses of each other. 2 and 4, 2 multiplied with 4 is equal to 1. 1 is multiplicative identity. So 2 and 4. Then similarly 3 and 5. Are inverses of each other. Are inverses of each other. This means that 2 is inverse of 4, 4 is inverse of 2, 3 is inverse of 5, 5 is inverse of 3, and 6 into 6 is equal to 1. So 6 is inverse of 6, or 6 is self-inverse. 6 is inverse of itself. And you know that identity is always inverse of identity. So inverses exist. So inverses exist with respect to multiplication modulo 7 exist in this particular set. And then fourthly, we observe that multiplication is commutative. Multiplication modulo 7 is commutative. And commutativity is very easily observable because symmetry of the table shows. Symmetry of the table, you can see that the table is symmetric. So symmetry of the table shows that multiplication is commutative. You can see these things. So multiplication modulo 7 is commutative, and associativity of this can be checked by inspection. Associativity of multiplication modulo 7 can be checked by inspection. So these observations make Z7 into Z7 minus 0 into a abelian group under multiplication modulo 7. Therefore Z7 minus 0 is a abelian group under multiplication modulo 7. So having observed that, finally we can check by inspection. Finally it can be checked. It is slightly lengthy process, but it can be checked very easily. It can be checked by inspection. That this particular binary operation, multiplication modulo 7, distributes over addition modulo 7, and hence Z7, which is in fact 0, 1, 2, 3, 4, 5, 6, is a field, and this is field under binary operations. Addition modulo 7 and multiplication modulo 7. So this is one of the examples for ZP being a field where P is a prime. So having said that, now let's come to the concept of polynomial rings, a ring of polynomials. So we are going to come to the concept of ring of polynomials or polynomial rings. So ring of polynomials. Ring of polynomials. So we consider following expressions. Consider following expressions. It's just to understand what a polynomial is. So consider following expressions. Two plus 6 times, let's say 6 times x minus 4 times x square plus 5x cube, then plus 9x raised to power 4. Let's call this is our first expression. Secondly, consider this expression minus 2 plus x minus 6x square plus 2x cube minus 4x raised to power 5 plus 13x raised to power 6. And let's take another expression. Let this be square root of 3, in fact radical of 3, minus 5x plus 4x square plus 2 upon 3 x cube. And let's consider another expression. Let this be 4 plus 3 times iota minus 4 times iota multiplied with x minus 5 plus 6 iota multiplied with x square plus 4 minus 3 iota multiplied with x cube. So these expressions are in fact polynomials. These are polynomials. These are polynomials. And you are very well aware of polynomials, because in your intermediate you have studied differentiation of polynomial functions, integration of polynomial functions. So the same thing. These expressions, when you convert these or name these as a function, these are polynomial functions, and you differentiate such functions at intermediate level. You also integrate them. So these are polynomials. Note that in this polynomial, 2, 6, minus 4, 5 and 9 are integers. In this polynomials, minus 2, minus 2, 1, minus 6, 2, minus 4, 13 are also integers. In this polynomial, radical of 3, minus 5, 4, 2 upon 3, these are real numbers. And in this polynomial, 4 plus 3 iota, 4 iota, 5 plus 6 iota, 4 minus 3 iota, these are complex numbers. So polynomial number 1 and 2, these are polynomials whose coefficients, these are called coefficients. So whose coefficients are integers. So these are polynomials over Z, the ring of integers. So let's observe these things. So we note that 1 and 2, 1 and 2, these two are polynomials over Z, the ring of integers. And the reason is because the coefficients, these are called coefficients 2, 6. So because coefficients 2, 6, minus 4, 5 and 9 are integers. So these coefficients belong to Z. And for second one, we note that minus 2, 1, minus 6, minus 2, 1, minus 6, 2, minus 4 and 13. These coefficients belong to Z, the ring of integers. So these polynomials are polynomials over Z, the ring of integers. So having said that, let's come to third polynomial. Third polynomial is polynomial over R, the ring of real numbers. So 3 is polynomial over R. This is the way we have decided to denote the ring of real numbers. So the reason is because the coefficients. Radical of 3 minus 5, 4 and 2 upon 3. These coefficients belong to ring of real numbers. And about this particular polynomial, this is polynomial over C, the ring of complex numbers, and 4 is polynomial over C, the ring of complex numbers. And the reason is because the coefficients 4 plus 3 iota minus 4 iota minus 5 plus 6 iota and 4